and regard this as the inner product of two states. The state I get from this path integral, the top one, and the state I get from the bottom path. Okay? Now the same quantity I could also obtain by putting the two Wilson line here and cutting it here. Okay? These are two different cuttings of the same path integral. Okay. Now, this guy, each of these factorizes onto some state. Okay? I don't know what the state is. I don't know what the state is, but remember the state is a state in Chern Simons theory on an S2. And what was the dimensionality of the Hilbert space of Chern Simons theory on an S2? 1. Right? So whatever this state is, it is some number times the vacuum state, because there's no other state in the theory. Okay? So this state is equal to some C1 times 0. Okay? This state is equal to some C2 times 0. Okay? And so now let's see. Suppose I take this quantity, which is this times this. Okay? This quantity, C1 and C2 turn out to be real numbers. Okay? So I won't worry about mod squares. This quantity is just C1 squared, because I'll assume that 0 is unit normalized. So it's C1 times 0 times C1 times 0. Okay? This quantity here is also C1 squared, because it's C1 times 0 with C1 times 0. Okay? But that quantity was the same as C2. Okay? So we've got that C2 is equal to C1 squared. Okay? But so we've proved that C2, so that's this guy, is equal to the square of this guy. Okay? I've done it in normalization in which the vacuum times vacuum is 1. If you undo that normalization, you will get an extra factor of this. Okay? So we've proved that the expectation value of two Wilson lines, unknotted Wilson lines, is the square of the expectation value of one Wilson line. Actually doing more complicated manipulations involving taking two Wilson lines together and taking two Wilson lines together, cutting it through a region where the thing passes through the Wilson lines and unknotting them in one Wilson line, Witten manages to find an expression for the expectation value for one of these Wilson lines. I'm just quoting the answer for you because we're going to use it. It turns out to be q to the power n by 2 minus q to the power minus n by 2 over q to the half minus q to the power minus half, where q is equal to e to the power I to 2 pi I by kappa. Okay? This turns out to be the answer. And you can just keep it at the back of your mind. We'll need it some part, late part in the next lecture. Okay, that's really all I want to say about pure Chern Simons theory. This ends my tutorials from the 1980s. Any questions or comments before we proceed? Excellent. Okay. Fine. So, in the end, there's only so much you can do with pure Chern Simons theory. You can win a Fields Medal or two, but okay. Now we want to get more interesting. Okay, so how do we get more interesting? You see, pure Chern Simons theory, as I've told you, is, from the point of view of quantum field theory, very trivial. It's not really quantum field theory. It doesn't have local degrees of freedom. Okay? Let's say we're interested in quantum field theory. We want local degrees of freedom. How do we Is there a way of making Chern Simons theory compatible with local degrees of freedom? Of course there's a way. You add matter. The Chern Simons degrees of freedom may not have local degrees, modes may not have local degrees of freedom, but the matter does. Okay, so add matter interacting with Chern Simons theories, and you get a theory with genuine local degrees of freedom. Okay, now, the idea of studying matter theories coupled to Chern Simons theory is far from new. Our condensed matter colleagues have been doing this from the 1980s. I'll give you a 5-minute review on what they've been doing and why they've been doing it, before turning to the issues of real interest to us. Okay, so the condensed matter people deal largely with abelian Chern Simons theories, k by 4 pi, ADA, U1 Chern Simons theory, and what they do is couple this Chern Simons theory to non-relativistic matter. Okay, now let me motivate what happens when they do this. You see, I told you that the equation of motion for Chern Simons theory was F is equal to 0, but when you add matter, that's no longer true. When you add matter, the equation of motion is k by 2 pi times F is equal to star of J matter. Because this is what you get by pairing this part of the Lagrangian with respect to A. And J matter is what you get when you vary the matter part of the Lagrangian with respect to A. Okay? So now let's look at the 1-2. The 1-2 component of this equation, space component of this equation. That's k F12 is equal to F12 is equal to 2 pi by k times J0. What does this mean? Suppose I've got a particle. Okay, I'm assuming that all particles have charge 1 here. Okay, suppose I've got a particle moving around. By this equation of motion, the particle carries charge. Its integrated charge is 1. By this equation of motion, it carries 1 unit of flux. Okay? Oh, sorry, not 1/k of a unit of flux. Okay? The integral of flux around it is 2 pi by k. Now, so suppose I've got one of these particles, it's interacting with Chern Simons, so it carries this flux. I take another particle around it. What happens? It picks up a phase. By the famous Aharonov-Bohm effect. I said that wrong. Okay. Okay. What is the phase? Well, it's just integral of Q, which is 1, ADL. ADL by Stokes' theorem is integral of F. Integral of F was 2 pi by k. So the phase was e to the power 2 pi by k times an I. This is the phase that you get when you take one particle around another. But as you know, you can interchange two particles by doing a rotation not of 2 pi but by pi. Okay? So the phase that you get when you exchange two particles is e to the power pi I by k. Okay, so when k is 1, this is pi, minus 1. So these particles, which were originally bosons, let's say, start behaving like fermions. But when k is anything else, you get a strange statistic when you interchange these particles. Okay? And this is a very interesting phenomenon that actually happens in condensed matter systems, fractional quantum Hall effect, for instance. The effective excitations do not have phase 1 or minus 1 when you take them around each other. They pick up funny phases. This is actually only consistent in 2 dimensions. Okay? And the particles that have this property are called anyons. And this quantity here, I will sometimes refer to this phase as nu. And that's called the anionic phase of the particle. Okay? So U1 Chern Simons theories, coupled to charge matter, turns the matter particles into anyons. So when you've got matter Chern Simons, this is the first lesson from our condensed matter colleagues. Matter Chern Simons theories, at least in the non-relativistic context, gives you theories of anyons. Okay? Now, you might wonder, what happens when everything here was abelian. Everything I said about this non-relativistic theory was abelian and so very boring. So relatively boring. And you might wonder what happens if I make the whole thing non-abelian. It's a slightly more involved calculation, worked out in papers by Jacques and Bach, and there were Lindays in the early 90s. But the answer is very simple, and I'll just go to it. So suppose you've got two particles in representation R1 and R2 of the gauge group. And I take them round each other in Chern Simons theory. You should get some sort of phase. What is the value of the phase? And the answer is that the phase is an operator. There's no one value. It depends on how the color indices of the two particles are oriented. In particular, given these guys, two particles R1 and R2, you can Krebs-Gordon couple them into a sum of representations Rn. Okay? And the phase that you get depends on which of these representations you've coupled them into. So if you couple them into neither, it will be some linear combination. And the answer turns out to be 1 by k, the quadratic Casimir of Rm minus the quadratic Casimir of R1 minus the quadratic Casimir of R2. I may have missed a factor of pi somewhere. Okay, I'll fix that as we actually use this one. Okay, and where did this come from? It's actually very simple. You see, if you imagine one gauge boson exchange between two particles, as you know very well, this is proportional to T dot T, T1 dot T2. But T1 dot T2 is T1 plus T2 the whole thing square, minus T1 square, minus T2 square. So that's quadratic Casimir of the representation couples to, minus the quadratic Casimir of the original representations. That's the basic place it comes from. This T dot T turns into the sum of Casimir. Okay? So, when you've got still non-relativistic, still quite simple, easy, very tractable things, non-relativistic particles interacting with the Chern Simons theory, you get what some people sometimes call non-abelian anyons. The phase you get when you take one guy around the other, it's not a number, it's an operator, whose eigenvalues are this.
K is kappa here.
K is kappa, sorry.
And suppose this can be understood from the OP of the primary to W.
It's exactly that, right. If you take it classically, right, in the classical.
So why is this phase determined just by one gluon exchange?
It's not determined just by one gluon exchange. Actually, the one gluon exchange would give you just the first term in that phase. You have to sum. But this problem is actually so simple because Chern Simons theory is exactly solvable theory. You can actually do this calculation. It's a non-relativistic quantum mechanics, so you don't even do it in this diagrammatic language. You do it by doing the constrained quantization of the system. Okay, you find the phase space. Okay, it's just something you can do exactly. This was motivation.
If you think of you think of the particle as creating a Wilson loop, and each Wilson loop is associated with a primary.
Exactly, this is the monodromy of one primary around another. That monodromy gets quantum corrections, meaning in the large scale limit, it's exactly this. That'll be, or maybe it's exactly this.
I think it is exactly.
Maybe it's exactly this even. Yeah, okay, maybe just, right, maybe it's exactly this. Yeah. Right. Okay, in fact, that's one way of understanding where that monodromy comes from. It's the Aronoff-Bohm effect. Okay, excellent. Other questions or comments? Fine. So, the last thing I wanted to say about the non-relativistic system is about a calculation you can do with this non-relativistic theory. You see, this system of anyons, especially the system of non-abelian anyons, is quite a complicated system, which is actually very hard to get your hands on. It looks very simple, right? I mean, there are no interactions except phases when particles go around each other, but those phases are not trivial. And just to give you a sense for what that means, let me present to you the answer of a classic calculation first done by Aronoff and Bohm in the 1940s or something like that, and then corrected by a guy named Reisenhaus, and the correction was really explained by Jacques and collaborators in the early 90s. There was a small thing that Aronoff and Bohm got wrong. Okay, and the calculation I'm going to do is to ask, suppose I've got this non-relativistic theory interacting with non-abelian Chern Simons theory, and I want to scatter one of these particles of the other. What's the S matrix? How do you do this calculation? Well, this calculation is terribly simple. You see, we're doing non-relativistic quantum mechanics, so we go to the center of mass. We factor out the center of mass degree of freedom and the relative degree of freedom. The relative degree of freedom becomes a one particle problem. The one particle problem becomes, in the right color, essentially scattering of a one particle of a magnetic flux tube. Okay, with the strength. Okay, and this calculation was done by Arnov and Bohm and then corrected by people in the, so you just look up the answer in the literature. Okay, and I'm just going to quote the answer to you and discuss certain aspects of it, which will be important for us. The answer turns out to be, so let's call this quantity nu, the effective phase. Actually, let's call the effective phase e to the power 2 pi I nu. Okay, so 2 pi I nu is the effective phase. Okay, so it's this quantity maybe with some pi's.
I think it's just an overall pi.
Maybe there's an overall pi. Okay. The answer turns out to be the following. Non-relativist Aharonov-Bohm scattering gives you the following strange result. I'm presenting the answer in the center of mass frame. Sorry, it'll take a minute to write down. Where A and R is some constant. I'll tell you about the constant amount. Okay, it's a very complicated answer. I mean, not by the standards of Zwieburn, okay, but nonetheless a very, very complicated answer. And why did I write such a complicated formula on the board? There are things I wanted to tell you about it.
What's P?
What is?
P.
Principal value. It's how to deal with the singularity of zero. Okay. Yeah. So, the first thing I want to tell you about this answer is that if you look at this, so what is this answer? This answer is a function of the center of mass energy. Okay? I've written these square root s's very fancily. In the non-relativistic theory, square root s is just twice the mass. But when we actually do the relativist calculation, it'll turn out, yeah, so just to write in a suggestive way. So it's an answer, the answer depends on the center of mass energy and the angle. Okay, all the interesting structures here are functions of the angle. So we get three structures. The first structure is cot theta by 2. The second structure is some complicated function of other stuff. K is the momentum. Okay, complicated stuff, function of the momentum, but constant in the angle. And the third structure is what's really interesting and what will play a stellar role through much of my talks, is this delta function. Okay? So the Arnav-Bohm answer just obtained by uncontroversially solving a Schrodinger equation, okay? No controversy about this, okay? Produces this answer including this delta function. Now, if you are tuned to scattering in relativistic theories, this delta function looks very odd because it's not analytical, okay? And you might somehow be unsatisfied. You might somehow be unsatisfied and wonder if all these people made a mistake when they did the calculation. Of course, you can easily check that they didn't. By the way, the people who made a big deal of this delta function were Jackie and collaborators. Jackie and collaborators really realized that this was an unusual thing and really explained how very carefully explained how that delta function was needed for unitarity. Without it, you don't have a unitary answer. Okay. This was like 20 years ago. Jackie and collaborators, including Dong-Soo Bak, who's done a lot of fantastic work on the non-relativistic Chern Simons theory. Okay. Okay. So now, but you might find this disquieting, and what I now want to give you is a physical interpretation that makes it clear why you should have expected such a delta function. Okay? It's a very simple physical interpretation, but as far as I know, nobody's at least published this before. But it's almost obvious, you can judge, but I think it's almost obvious that it's correct once you said it. And the answer, the thing is this, look, when you are scattering, there are two things that happen. Dominantly, nothing happens. That's the identity piece in the scattering matrix, at least if you've got no IR divergence. And then you get some scattering. So the scattering matrix is identity plus I times some t. Okay? The point is that when nothing happens, you've got to wait back, it just goes through. It comes out with the same amplitude that you sent it with. That's why you get identity times t. But now let's look at this context where we are scattering in 2 dimensions of a magnetic field. We've got this little lump, and we send it through. Okay? Half of the lump goes from above the scatterer. Half of the lump goes from below the scatterer. Nothing happens. It just goes through. But as it goes through, this part and this part pick up a phase. The phase picked up by this part is e to the power I pi nu. The phase picked up by this part is e to the power minus I pi nu. Each of these is half of what went in. So what comes out is half of e to the power I pi nu plus e to the power minus I pi nu times what comes out is this times what went in, which is equal to cos pi nu. So if you were tuned to the physics of the problem, you would not have set up scattering as identity plus T matrix. You would have set up scattering as cos pi nu plus T matrix. But of course, that's not what scattering formalism does. It sets up the problem as identity plus T matrix. So if you do it that way, do it this wrong way, what you will find is 1 minus cos pi nu in the S matrix, and that's exactly, you can check that it comes with the right sign, the right factors, to totally turn this into cos pi nu times identity plus everything else. Okay? This is very simple, but very important in my opinion. A very simple and very important qualitative fact whose explanation, though we see it quantitatively in the non-relativistic theory, the explanation for this fact is universal and should apply also to the relativistic theory. Phase plus phase gives cos. Okay? This unusual fact, unusual strange feature, if you set up S matrices traditionally, is just a fact, and a consequence of the fact that we're dealing with anyons rather than bosons or fermions. That's basically what's going on. Okay? Fine. And then there are all kinds of other aspects of this formula that I will, some of which I have need for later, but I will not introduce now because I'm running out of time. We'll come to it later. I just have to say one word. There's this parameter W, in the problem that enters the formula. I haven't told you what that is. You see, let me say this. When I look at the scattering between two particles with an Aronoff-Bohm phase, I haven't completely specified the problem. Because it's possible that in addition to particles picking up phase as they go around each other, they could have a point-like interaction when they touch. Okay? And indeed, in our quantum field theory situations, because we've got interaction terms, there will be the analog of these pieces. Okay? Now, in papers by Bach and Camillo, the effect of these point-like interactions was figured out in terms of an effective boundary conditions at zero, near the flux, and this W parameter is something that parameterizes either the strength of the point-like interaction or, more clearly, just the effective boundary conditions near zero. So one parameter set of allowed boundary conditions gives you nice self-adjoint quantum mechanics, and depending on what that parameter is, you get, the details change. We will need this as we go along in the future. At the moment, it's some complicated stuff. Okay.
So if we're sure that we're scattering bosons and fermions, then this will not be appear.
If we're sure that we're scattering bosons and fermions, this delta function will not appear. Yes. But, you see, if you're scattering what were bosons and fermions in the absence of the Chern Simons theory, then there will never be bosons and fermions when you scatter. Right? So, you have to be sure that the actual physical things are bosons and fermions, not what you study. Okay. Other questions or comments? Excellent. Fine. So, this is all I wanted to say about non-relativistic physics. This ends my second tutorial from the 1980s and early 1990s. Now we will graduate to the 2000s. Okay. Any questions or comments? Fine. So we've dealt with exact solutions of a relativistic theory, but it wasn't a quantum field theory, it was N Chern Simons theory. And we've done a lot of condensed matter stuff, but didn't you study string theory because you didn't want to do condensed matter physics? So now we've got to get more interesting. We've got to start talking about relativistic quantum field theories, which of course are much more interesting than non-relativistic theories because they allow for particle production. It's much more complicated and interesting effect than fixed particle number theories. Okay. So, now, what we're going to start doing is to study matter-Chern Simons theories. Okay? Relativistic matter-Chern Simons theories. And see if there's anything interesting that happens generically first in the study of these theories and then get more specialized. Okay. The first thing that is clear once you think about studying matter-Chern Simons theories for 1 minute is that these theories have specially simple renormalization properties. And the specially simple renormalization property that I'm talking about is that K, which is the analog of 1 by G squared Yang-Mills, the analog of that, cannot be renormalized. Let me give you two arguments for this. The first one's a very simple argument. It's that K is an integer. And an integer cannot be continuously renormalized because an integer is discrete. Okay? So if you do everything in a manner that preserves gauge invariance, if you turn an integer into non-integer, you've violated gauge, you've done something wrong. So if the theory can be defined, must be possible to define in a way that K does not get renormalized. There is another related argument that is the technical reason for why the renormalization doesn't happen. It's that, when you get infinities, you cancel them by